This is the video for our CVPR 2023 paper, LargeKernel3D, Scaling Up Kernels in 3D Sparse CNNs. Recent advance in 2D CNNs has revealed that large kernels are important. However, when directly applying large convolutional kernels in 3D CNNs, severe difficulties are met. To address this vital challenge, we instead propose the spatial-wise partition convolution and its large kernel module. We first analyze the difficulties of 3D large kernel CNN design in two aspects. The first challenge is efficiency. It is easy to understand that 3D convolution is with the cubic kernel size and computation increases fast. For example, the model size increases 10 plus times when kernels change from 3 times 3 times 3 to 7 times 7 times 7. The second difficulty exists in the optimization procedure. 3D datasets may contain only thousands of scenes, which cannot match 2D image benchmarks in terms of scales. In addition, 3D point clouds or voxels are sparse, instead of dense images. Thus, it might be insufficient to optimize the proliferated parameters of large kernels and leads to overfitting. In this paper, we propose spatial-wise partition convolution as the 3D large kernel design. It is a new family of group convolution by sharing weights among spatially adjacent locations, rather than depth-wise convolution of channel-level groups. Spatial-wise partition convolution remaps a large kernel, 7 times 7, as a small one, 3 times 3, via grouping spatial neighbors, while the absolutely large spatial size remains unchanged. With regard to the efficiency issue, it occupies few model sizes to keep parameters the same as those of small kernels. Moreover, it takes less latency, compared with plain large kernel counterparts. As for the optimization challenge, weight sharing among spatial dimensions gives parameters more chance to update and overcome the overfitting issue. Considering that the spatial-wise partition convolution is designed in a sharing weights manner against the spatial sparsity. Although this design is efficient, there is still an issue. Voxels within an area share the same weight, which results in local details blurred. This phenomenon is further amplified with an increase of kernel sizes. To address this problem, we propose the kernel-wise position embedding. We compare the efficiency between plain 3D submanifold sparse convolution and ours. Our 3D large kernel networks achieve decent improvement on both semantic segmentation and object detection tasks. For the first time, we show that 3D large kernels can be realized efficiently and effectively. We also visualize effective receptive fields of plain 3D CNN, plain 3D CNN 2 times and our large kernel 3D for 3D object detection. The plain 3D CNN backbone has insufficient ERF size, which hardly covers a nearby car. Plain 3D CNN 2 times is a deeper version with its layers doubled in each stage. More layers help little in ERF, as the disconnection between sparse features. Our large kernel 3D obtains large ERF at both the object centers and edges, capturing context information. In this paper, we further propose large kernel 3D for 3D semantic segmentation and object detection. For the first time, we show that 3D large kernels can be realized efficiently and effectively. We expect our findings to advance further development of 3D networks. Thanks for your listening.